All right, so in this video, we're going to take a look at a problem that is an extension of the extreme value theorem, where if we are given a continuous function on a closed interval, closed and bounded region now in Calc 3, then we are guaranteed both an absolute max and an absolute min, and it's going to be our job to find it. So fortunately, the process isn't very different from what we've seen in the previous video and what you've done in Calc 1. There are going to be some slight additional things that we need to take into consideration, though. So to get things started, we know that these critical values, these absolute maxes and mins, could occur at interior points and along the boundary. So for the interior points, we'll look at the critical values. That's going to have us investigating f sub x set equal to 0 and f sub y set equal to 0. So the partial derivative of f with respect to x is going to give us a y minus 1, and with respect to y, that's going to give us an x minus 1. Now, both set equal to 0 pretty quickly give us a interior point of 1, 1. Now, I do want to confirm that it is in fact an interior point, so let me go ahead and sketch my region. So my region is going to look something like this, where I have 0, 0 as a point, 2, 0, and 0, 4. So that's a 4, that's a 0, that's a 2. And this is going to be my region now. This is going to be my R. And in fact, the point 1, 1 is interior to it. Okay, so now picture what's going on here, okay? This z-axis is coming out at us. It's very difficult for me to draw on a screen, but the z-axis picture is coming out at us. Above the screen is the surface floating around. The surface above this is where we're searching for the absolute max and the absolute min. The point 1, 1 is interior to it, so I know it is something that I would need to investigate and look into a little more closely, okay? Now, in Calc 1, we tested the endpoints of the closed interval. Well, now we don't have specific endpoints of the closed interval, we have boundaries. So I need to investigate what's happening along the boundaries of this. Now, the equations themselves aren't going to be too hard to come up with. This is clearly going to be where y equals 0. This is going to be where x equals 0. And then to come up with this equation of the line, you can do that however you'd like. Seeing as we're in Calc 3, I'm not going to really spend a whole lot of time reminding you how to do that. But that's going to be our equation of the line. So we need to check out all three of these to see if there's any issues. So let me show you what's going on. I'll start with y equals 0. Okay, so I'm going to test along this area right here, this line. If y equals 0, then we're going to have f of x 0, and I'm going to come back up here, and every place I see a y, I'm going to put a 0. So that's going to give me negative x plus 3. Now I'm down to single variable. So if I take the derivative as I did in Calc 1, and I set it equal to 0 in hopes of finding more critical values, in this particular case, negative 1 doesn't equal 0, so nothing comes of it. All right, let's try x equals 0. I'm going to have now a function where we have f of 0y, which would be a negative y plus 3 if I let my x equal 0 there and there. My f prime of y is now going to be a negative 1 again. If I set that equal to 0, I get nothing. Now, let me scoot the screen up a little bit. And let's check out y equals 4 minus 2x. So now the function is going to be a function of x and 4 minus 2x. So plugging that in, plugging 4 minus 2x, that is, in for y, is going to leave us with this. And then if I simplify this down, my f of x is going to be negative 2x squared plus 5x minus 1. So all I did was I plugged this guy right here in for y, back up there, plugged it in there, and then I simplified all this down to this. When I now take the derivative of it, since I'm down to a single variable, that's going to give me a negative 4x plus 5. When I set that equal to 0, I actually do get a 5/4. So what that means is this is a number that I still need to consider when it comes to my possible absolute max and absolute min. Now, I remember I'm going to be testing at points. Just like I have a 1, 1 up here, I'm going to need a point right here. So if our x value is 5/4, the y value could be found by plugging that in right here, giving us 3/2. So this is going to be something I need to consider along with this right here. Additionally, I need to consider the vertices given. So the 0, 0, the 2, 0, and the 0, 4 are kind of acting like those endpoints from Calc 1. So there's going to be, looks like 5 different points that I need to test. So let me go ahead and move the screen up and see if I can include all of that. Hopefully it's still readable. But in Calc 1, we made a table, and I'll make a table again in Calc 3. Where now we're testing 1, 1. That was our interior point. Had this been a point outside of the region, we would have excluded it. We're only interested in what's happening here. We'll test the 5/4, 3/2. Then we'll also test the endpoints 0, 0, 2, 0, and 0, 4 given in the problem. So we're taking these values right here. We're plugging them in to the original function, and it's spitting out the z coordinate. So when I do that, I get a 2. I get something that's approximately 2.125, a 3, a 1, and a -1, which means that this guy here is the absolute max, and this guy here is the absolute min. So hopefully you can see how it's very, very similar to the same foundation you saw in Calc 1, only now we have to take it a little bit further considering we're up in a higher dimension and we're talking about regions now and not just intervals. All right, so we're going to take a look at an application that you would have seen in Calc 1 as well, now brought up into R3. We're going to maximize the volume of a rectangular prism inscribed inside a hemisphere. I always work in Calc 1 problems where we maximize the area of a rectangle inside of a circle. This is, again, just taking it up a little bit, but the same basic idea. Now, I've drawn this picture in such a way so that it's a little bit easier to make mention of a few things and work with a few things. First of all, I'm going to go ahead and say that the equation of the sphere, and I know it says hemisphere, but I'm going to say the equation of the sphere for now, is x squared plus y squared plus z squared equals r squared. Seeing as we only want half of that, I'm going to go ahead and solve it for z and avoid the plus or minus. So z is going to be r squared minus x squared minus y squared. Okay? And that's important because now we can identify this point as xy, the square root of r squared minus x squared minus y squared. And again, just like we would have done in Calc 1. Now, the other thing that I've constructed the picture to help us out with is by putting this center at 0, 0, 0. That's going to help us with the x's, the y's, and then of course the z. So the center of this box should move out an equidistant along the y-axis on the positive side as the negative side. Same thing with x. It's centered right in the middle, so it should come out an equal distance along the x-axis, as positive x-axis, as it does the negative x-axis, which means that the volume is going to be 2x times 2y times z. So now the volume function itself is actually going to be a volume function of x and y. Remember in Calc 1 we always started with more variables and we'd whittled it down to 1. Now we've got 3 variables, we're bringing it back down into 2. That's going to give us now a 4xy, and then the z was the r squared minus x squared minus y squared. So this is the function right here that we want to optimize. So let me go ahead and do that over here to the side. We'll take our v sub x, which is going to be the derivative of this guy, of course, with respect to x. I would treat this as a product rule, where this is the first and this is the second. So with respect to x, the derivative of the first would be 4y. Then we have our square root, r squared minus x squared minus y squared. And then plus derivative of the second back times the first. So there's the first. And then for the derivative of this is going to be 1/2. Maybe I'll write it here on the side separately. 1/2, keep the inside the same, subtract 1, and then back times the derivative of the inside with respect to x, which would be a negative 2x. So when I put that together over here, that's going to be the negative 2x there, and then in the denominator, we'll have our 2 with our square root of r squared minus x squared minus y squared. Now, I'll go ahead and I'll tackle this one first, and then I'll mention the second one briefly, and I think I can convince you how to save a little work. So now we know that we're going to set this equal to 0, and in order to make any kind of headway in this whatsoever, what I'm going to do is get rid of my constants as best I can here. I know that I've got the 2's go away there, and then the 4's there can be divided off, so the constants are gone, and then I'm going to move this guy over to the other side. So that's going to leave me with y square root r squared minus x squared minus y squared equals x squared y over the square root of r squared minus x squared minus y squared. I'll then go ahead and multiply this guy over. And guys, in simplifying this, there's a lot of it that's going to be left up to you, so feel free to be creative and do what works best for you. X squared y. Additionally, now, because I know that y is a dimension, it can't be 0, I can see that r squared minus x squared minus y squared has to equal x squared. So I essentially just divided the y off. Now for a couple really important observations. The first one is this. The first one says that from up here, we know that z equals the square root of that, which means that z squared would equal r squared minus x squared minus y squared. So if I substitute that in right there for z squared equals x squared, we can tell that x would have to equal z. Now, pluses and minuses don't matter because, again, they're dimensions. So we can see that x would equal z. Now, to take it a little bit further and saving us some work, if you come back and you look at this derivative right here, when you take the derivative with respect to y, not a whole lot is going to change other than the ordering of the variables. If I go with respect to y, my first is going to be 4x, but then that's going to be the same. But then on the back side here, this is going to be a negative 2y. And so the only real difference is if you wrote that out and worked it down, you would essentially be dividing off an x here instead of a y, but you would also then be left with an r squared minus x squared minus y squared equals a y squared. Therefore, z squared equals y squared and z equals y. Now, if you don't believe me, that's perfectly reasonable. Go ahead and work out, if you will, v sub y, set it equal to 0, and I promise you what I explained will happen. Because those variables will be different, and that's the only thing, you'll be dividing off an x here and be left with a y squared there, making that same substitution. We find out that z equals y. All right, so let me move this up a little bit here. Now, we know that from the transitive property, if x equals z and z equals y, that of course x has to equal y has to equal z. So if I take this z squared, which equals r squared minus x squared minus y squared, knowing that x equals y equals z, I can then say my x squared equals r squared minus x squared, which is 3x squared equals r squared, which says that x equals r over root 3, which must also equal y, which must also equal z. So if we're searching for the volume now, and that volume was, let me move it back up here, that volume was this guy right here. If I take what I now know as x, y, and z, I'm going to have 2 times r over root 3 times 2 times r over root 3 times r over root 3 to get 4r cubed over 3 root 3. So that is the maximum volume of the rectangular prism that can be inscribed inside of a half sphere or a hemisphere. Now, as you look back and really pay close attention to what we did, it's no different than Calc 1, and if you need to go back and watch your Calc 1 notes, I would strongly encourage you to do so. We came up with our formulas. We whittled it down from 3 variables, x's, y's, and z's, into 2 by making the substitution we did. And then from there, we attempted for the v sub x and the v sub y. The v sub x we were pretty clever with, which allowed us to avoid much of the v sub y, but still giving us the desired result. Once we got to that, we were able then to go back into what it is we were looking for, come up with our values for x, y, and z, and then substitute that back in to get the actual volume, the actual maximum volume for that rectangular prism.